Welcome to the Module 6 project, a fair contest between machine learning models. You have met 7 classical algorithms. Now the real skill, not memorizing them, but knowing which one to trust for a given job, and how to compare them honestly. Our job today, decide who is likely to default on a loan. First, why this decision is hard. There are 2 very different ways to be wrong. Approve a loan that then defaults, and the bank loses money. But reject a borrower who would have repaid, and you lose a good customer to a competitor. A model that is simply accurate might still make exactly the wrong kind of mistake. So we will have to choose our yardstick with care. Here is the data. 2,400 past loans, each described by 6 features: income, loan amount, debt to income, credit score, years employed, and past delinquencies. And crucially, each one is labeled, did it default, or was it repaid? But look at the balance. Only about 23% defaulted. That imbalance is a trap, as we are about to see. Before any fancy model, we set a baseline. The laziest possible rule: predict that everyone repays. Let us score it honestly with a confusion matrix. It gets every repaid loan right, so its accuracy is 76%. That sounds respectable. But watch the defaulters. It catches 0 of them. 0. A model can look accurate and be completely useless. That is why accuracy alone must never be trusted on imbalanced data, and why every real model has to beat this bar. Now our contenders, 6 classical models, each with a superpower. Logistic regression, a simple linear baseline, k nearest neighbors, which trusts whoever is closest. A decision tree, a chain of yes or no questions. A support vector machine, which finds the widest margin. And 2 ensembles of trees, a random forest, and gradient boosting. Which should we believe? We will not guess. We will measure. A comparison is only fair if every model faces exactly the same test. So we split the data once, and seal a test set away in a vault. No model may see it until the very end. On the rest, we use 5-fold cross-validation, the same 5 folds, scored with the same metric, for every single model. Same data, same folds, same yardstick. Now the contest is fair. Let the contest run. Each bar grows to that model's real cross-validated score, the area under the R, O, C curve, where higher is better and the baseline sits at 1/2. Logistic regression clears the bar at 0.78, KNN and the tree, about 0.79. The R, B, F, support vector machine trails at 0.77. Then the ensembles pull ahead, the random forest at 0.80, and gradient boosting takes the crown at 0.81. On tabular data like this, ensembles of trees usually win. But why do they win? Let us look at just 2 features, debt to income and credit score. The real danger lives in a corner. Borrowers with high debt and low credit default far more often. Logistic regression can only draw one straight line, and no single straight line can fence off that corner without wrongly condemning good borrowers too. A tree, though, makes axis-aligned cuts. One split on debt, another on credit, and it boxes the danger zone in exactly. An ensemble combines many such boxes, which is why it captures patterns the line simply cannot. Score is not the only axis. Each model also has a cost, and a very different level of transparency. Logistic regression and a single tree train fast and are easy to read. K nearest neighbors barely trains at all, but is slow at prediction time. It must compare every new borrower to the whole dataset, and the ensembles are the most expensive to train, and the hardest to explain. So the fastest, clearest model and the most accurate model are often not the same model. Which one matters more depends on the job. Now, the right yardstick. For lending, the mistake that hurts is missing a defaulter, so we care about recall, the share of true defaulters we actually catch. Compare the confusion matrices. The baseline caught none. Our gradient boosting winner now catches a large share of them. But there is a tension. Push recall too hard and you start rejecting good borrowers, hurting precision. The right balance is a business decision, not a mathematical one. So which model do we ship? It depends on the constraint. If pure predictive power is all that matters, gradient boosting wins. But a bank is legally required to explain every denial to the customer. A gradient-boosted ensemble of hundreds of trees is very hard to explain. A single decision tree, or logistic regression, can be read like a sentence, at only a small cost in accuracy. For loans, that transparency may be worth more than the last % of score. And the whole contest is just a few lines of code. Put every model in a dictionary, then loop, scoring each one with cross-validation on the very same folds. One loop gives you a fair, honest leaderboard. Let us tie it together. To compare models properly, always beat a baseline, and never trust accuracy alone on imbalanced data. Give every model the same split, the same folds, and the same metric. Expect tree ensembles to lead on tabular data. And remember, the highest score is not always the right choice. Match the model to the decision. That is how a professional chooses.